Welcome to this introduction to forecasting methods for renewable energy generation. In particular, today we will see wind energy forecasting of wind farms. Many of the techniques we will cover are in common with other renewable energy sources based on weather forecasting, such as photovoltaics and hydroelectric. The topic is developed within the Everest project, which aims at developing a holistic design environment that simplifies the programmability of high-performance big data analytics for heterogeneous, distributed, scalable, and secure systems. Within the Everest project, we have developed an application from scratch for wind energy forecasting. The application is designed to respond to the requests of a trader who dispatches the energy produced by one or more plants and must sell the energy on the market. The application will exploit the Everest design environment in terms of performance, computing capacity, and in terms of orchestration of the entire workflow. The Everest approach will be validated on two other industry-relevant applications. An application for monitoring air quality to program the production of industrial plants in order to minimize the impact of pollutions, and an application for vehicle traffic modeling designed to manage traffic congestion. Let's see the main topics of this presentation. We will start with an introduction to the energy transition and some numbers on the growth of renewables, in particular related to wind power. Then a brief introduction to the electricity market, a description of the variable renewable energy peculiarities, then we will see the main features of the service for the wind power forecasting available in the market. Then we will go on with the description of the metrics used to evaluate the performance of a wind forecasting tool. And finally, we will see the different phases of application development within the Everest project, the challenges faced, and the first results obtained. As we know, the growth of renewable energy sources is at the heart of the energy transition towards a sustainable system. Wind and photovoltaic energy play a primary role in this growth, if we consider that in 2019, 2/3 of the generation growth was due to wind and photovoltaic sources. The objectives set for 2030 foresee that half of the demand will have to be met by renewables. But as we can see in this graph, the growth of wind installations will have to accelerate considerably to achieve the goals set, so a great increase of installations is expected. As you can see, in recent years, the growth of wind power plant installations around the world has been continuous and more than linear. A positive point is related to the growth of the wind farms installations in the pandemic period, year 2020, much higher than in the previous year, around double. To understand the requirements of a forecasting application, we need to know the rudiments of the electricity market. The goal of a power producer or a trader who dispatches energy is to sell energy on the markets, and in this case we are focusing on short-term markets. There are three main types of short-term markets. The day-ahead market, in Italian called MGP, where hourly volumes can be programmed for the day ahead. The intraday market, with sessions following the MGP, where the volumes sold in the day-ahead market can be adjusted. And last but not least, the dispatching services market, managed by the transmission system operator, in Italy Terna, to balance the energy system and avoid congestions, sending orders to producers to increase or lower their generations. Most of the energy volumes are sold or bought in MGP. In this slide, you can see the experience of the several sessions. The intraday ones are called complementary regional intraday auctions. Recently, the continuous market sessions, called XBID, have been introduced in Italy, in a similar way to other European countries. These kind of markets are very important for the scheduling of generations from renewables like wind power and photovoltaic, exploiting the last updates of meteorological models. There is a main classification among the energy sources that distinguishes programmable from non-programmable sources. The meaning is that if a power plant can follow the energy demand, it is considered programmable. Of course, wind generation depends on weather conditions and is the most intermittent source of energy, defined as a variable renewable energy. In the last years, the fast integration of VRE, such as wind and solar sources, has improved the challenges in charge of the TSO to balance the grid and to need to use thermoelectric plants to reduce demands in the dispatching processes. Of course, as a consequence of the increase of generation by VRE sources, it becomes important to encourage conventional electricity sources to produce energy on demand and to increase their availability and flexibility, understood as speed in responding to dispatching orders. Of course, these services have a cost, paid by traders and producers, and final customers. To reduce these unbalanced costs, it is necessary to minimize the forecasting error related to the volumes sold in the markets. For this reason, it's crucial to exploit a state-of-the-art services for wind and photovoltaic energy forecasting for our portfolio. The challenges related to the variability of wind and solar generation put different challenges to the operators, depending on their role in the energy system. Wind farm owners have to program their maintenance operations with a long-term horizon. The transmission system operators, like Terna, have to balance the grid in real time. Traders, as explained, have to forecast the volumes to sell in a short-term horizon, trying to minimize the forecasting errors that can be translated in high imbalances costs. The result has an impact on the price recognized by the producer or paid by the final customer. On the market, there are several service providers who specialize in wind and solar energy forecasting. The quality of service in terms of forecast accuracy can vary greatly depending on the provider, but also on the individual wind farm. The inputs required from the wind farm are usually the same: coordinates and power capacity of the wind turbines, time series of hourly generation, availability, curtailments by TSO, and wind speed measured by field anemometers. Every service provider uses several weather models and has his own algorithm to learn the function to predict the hourly generation. Of course, these algorithms are property of the service provider, so the process of calculation is a black box for the service user. Any provider service is able to follow the several sessions of the intraday markets. So it's possible for the operator to adjust the volume sold. Now, a brief explanation of the methods used to evaluate the accuracy of wind power forecasting. In literature, there are several metrics suitable to assess the quality of the forecast, each one with different features. In our case, according to our experience, we choose mean absolute error, very common and recommended in particular for wind power forecasting. To make a comparison with different wind farms results, MAE typically is normalized, dividing by the power capacity of the wind farm. Another metric used is normalized bias, the standard deviation from a mean value, useful to identify systematic errors. In this slide, you can find the mathematical definitions of these metrics. The absolute error is the absolute value of the difference between the forecasted and observed values. In this slide, you can see the workflow of the application developed in the context of the Everest project. The meteorological inputs are from Weather Research and Forecasting Model, WRF, a community-based model enriched with data simulation from several sources. The weather forecasts are combined with technical parameters and historical data of the wind farms by artificial intelligence algorithms based on machine learning techniques. WRF model has the task to simulate the evolution of meteo parameters, first of all, in our case, wind speed, in the short-time horizon compliant with the energy market sessions. The main advantages of this model are based on high-resolution grid, small up to 2.5 kilometers, and exploitation of several global observations from satellites, radar, and weather stations. The wind farm data used by the application are physical parameters of the wind farm, power installed, hub height, and wind farm time series, like hourly power generation, hourly wind speed from local anemometer, hourly power availability due to maintenance or failure of the wind turbines, and finally hourly power curtailment by the transmission system operator. In this workflow, the different steps of the application are detailed in an operational scenario related to the day-ahead market. Every day, the world forecast data for the day ahead are available for the power forecast and are collected in the storage. Step 1. These forecasts relate to the entire Italian nation, so it's necessary to select the WRF data related to the coordinates of our wind farm, as you can see in the step 2. Then the model combines the updated weather dataset with the physical parameters of the wind turbines and with observation data from the wind farms, preprocessing the data with the noising rules based on the power curve of the turbine. In the step 3, the clean data are used to update the training dataset of the machine learning algorithm and finally used to predict the hourly power generation of the day ahead. In the development of a forecasting application, it's essential to identify the most challenging modules in terms of volumes of data managed and calculation time. In our case, the most resource-hungry part is certainly the WRF weather forecast. If we consider that the forecast for one day occupies a volume of 6 gigabytes, while the energy forecasts of a day takes up a few kilobytes. Therefore, it's essential to concentrate resources on the acceleration of work in order to make the model suitable for managing the different intraday market windows. Furthermore, the acceleration of weather models can open the doors to widely used probabilistic methods in order to improve the accuracy of forecasts, such as ensemble methods. Regarding the ML algorithms, we can see that training and calibration activities requires at least 1 year of historical data, weather plus wind farm time series. The more the better, of course. Implementing real-time data could add value, improving forecast accuracy for the next closest hours, exploiting hourly generation and wind speed by field anemometer if available, in order to extract value from the intraday or continuous markets. Another issue to face is the quality of data from the wind farms. Often, the TSOs, turbine availability records, or dispatching orders are not complete or accurate, resulting in incorrect data that, if used for model training, can have negative impact on forecast accuracy. If we are using real-time observation data from the wind farms, another point is the unstructured data to manage. As a consequence, it's crucial to establish pre-processing rules to maintain a high level of quality of the dataset used for the training of our application, excluding bad samples. We decided to use the power curve of the wind turbine manufacturer as a filter to exclude data not congruent, identifying confidence intervals showed in the graphic in red. Now let's see some results obtained by our application related to a wind farm in Sardinia region for Jan 2021. The forecast curve from our application is shown in blue, while in magenta you can see the forecast by a reference provider, leader in Europe for wind forecasting services, and in green the observation data from the wind farm. It's difficult to evaluate the difference between the two forecasting data watching the graphic, but we are not far to the accuracy of the reference provider. In this slide, you can see the curves related to a month with higher wind power generations. In general, it's hard to obtain a good level of accuracy in the peak of the observation curves, because every model in these conditions tends to underestimate. In summary, to validate the results obtained, we followed several steps. The identification of the best key performance indicators to evaluate the forecast accuracy in comparison with the results obtained by a benchmark forecast provider. The data collection and preprocessing with the target to achieve the highest amount of historical time series with the highest accuracy as possible for training models in the right way, excluding bad samples. The machine learning algorithm selection, suitable the features of data typically available for our forecasting applications, in terms of quality and amount of data. Increasing the amount of data available, we expect to improve the accuracy of results. In general, as every forecasting application, the accuracy results can be improved identifying the weak points of the entire workflow in terms of data quality or algorithm settings. To reach this goal, it's crucial an in-depth study of the quality of the data, which in turn requires an in-depth knowledge of the data chain. Finally, here is a summary of the characteristics of an application for power forecasting from variable renewable energy in line with the definition of big data application. A state-of-the-art application for variable renewable energy forecasting relies on a weather forecast on a local scale with a number of daily runs optimized in terms of the weather model's updates and of the intraday market sessions, implementing a probabilistic approach. There is a challenge about the volume of data to manage, mainly related to weather data. A real-time data streaming from meters and sensors of the power plant, in addition to historical time series, to improve forecast accuracy considering the most recent data. The application must be fast to implement these real-time data. A pre-processing intelligence for real-time denoising and exclusion of bad samples to maintain a high level of input data quality. It's crucial the veracity of data used to train models. The capability of managing heterogeneous and unstructured data related to different features and formats. The application must manage a variety of heterogeneous data. A self-learning intelligence combining all the data collected to find the best weights for each specific wind farm or photovoltaic solar plant. The application can be used for different sites thanks to machine learning algorithms. A scalable and flexible tool ready to extract value from the current and future energy markets. The application must be developed to extract value in the electricity markets of today and tomorrow. Thank you very much for your attention.